This is the video for pre-lecture 3. So today we're going to be discussing mapping. And so mapping is a function or operation that takes us from our current state, x sub n generally, to our next state, x sub n plus 1. And this is done using some sort of function for our class. And so we're going to say that our next state, x sub n plus 1, is equal to that function f of our current state, x sub n, and maybe a parameter lambda. So let's do a basic example. So let's say our function, f, is going to be just a function of x sub n, our current state, no parameters for today, is going to be equal to 2 times x sub n times 1 minus x sub n. Well, graphically, what does this look like? Well, if we were to plot this up, this would be a parabola starting at 0, ending at 1, and having a maximum at roughly a half. So it looks something like this. Okay? Well, how would we use this map? Well, let's say we start off with our initial state, x1, is at a position of 1/4. We would take this current state and plug it into our function. So we say, okay, well, x2 then is equal to 2 times our current state, 1/4, times 1 minus our current state, which is 1/4, and that is going to be equal to 3/8. So graphically, that's going to say, okay, well, we start at roughly the 1/4 point here. And we go up to our function. And that gets us to this position here, which is roughly 3/8. Okay? Well, then we could apply this map again. x3 is going to be equal to 2 times our new state, which is 3/8, times 1 minus 3/8. And it can be shown that this is equal to 15 over 32. Well, graphically, how does this work? Well, if we draw a line connecting our 0, 0 position to our 1, 1 position, draw a straight line between those two, what we could do then is say, okay, well, I'm going to start at my x1 position, go up to my function, and that's going to give me my x2 position. So then I could take this x2 position and go over to my red line, bounce off the red line, go up to my function again, and this would give me my x3 position. I could repeat this process to get an x4 position, and continue that as many steps as we'd like. But we notice a couple things. It seems that we've taken this initial position at 1/4, and we seem to be moving towards the position at a half. This lends itself to the idea of a fixed point. So a fixed point, x star, is any state that maps to itself. So this is going to satisfy the function x star is equal to f of x star. Well, again, let's return to our example. So that would say then that our fixed point values x star are equal to 2 times our x star value times 1 minus x star, where all I've done is I've taken my initial map and changed out my xn and my xn plus 1 values with x star values. Now I need to go ahead and solve this equation. So that's going to be x star is equal to 2x star minus 2x star squared. Can rearrange, and that'll be then just 2x star squared is equal to x star. Well, this equation has two solutions. The solutions are x star being 0 or a half. And graphically, if we look back at our map, this corresponds to the 2 points where our function intersects that line representing the set of points where our map value of our current state would be our next state. So that graphically makes sense then. Okay. Well, if we notice, we seem to be moving towards one fixed point and away from the other, although this is sort of a general observation at this point. How can we maybe formalize that idea, because it lends itself to an idea of stability? So fixed point stability. If we start near a fixed point, we have a couple options. We either move away from the fixed point, so it would be unstable, or we move towards the fixed point, in which case it would be stable. We can think of this a little bit from a physical perspective by imagining a pendulum. So we have a pendulum. And what would a fixed point represent of the pendulum? A fixed point would represent any state where we don't move. We just stay in that state. And so we know that if gravity is operating in the vertical direction, then if our pendulum is just hanging vertically down, this would be a stable state. If there are no external forces, the pendulum is going to just continue to rest at its minimum position. So this would be an example of a stable fixed, well, this would be an example of a fixed point. The question of stability then comes in of what happens if we take our pendulum and perturb it slightly away from its position of fixed point. Well, we know for a perfect pendulum, this would just oscillate back and forth, but most pendulums have some degree of loss or dissipation in the system, and so we know that any physical pendulum is eventually going to return to its minimum position. And so this fixed point would be an example of a stable fixed point. But is it the only fixed point? Well, if we were able to perfectly balance our pendulum and there were no external forces, it's possible to have this position where the pendulum is at its maximum position. This would also be a fixed point. But we know that if we were to perturb the system in any way, we would move away from that maximum position and eventually swing back down towards our minimum position. And so this would be an example of an unstable fixed point. Well, so that's a physical representation of what's going on. Let's consider this from a mathematical perspective. So for stability analysis, we can test what the perturbation does by starting at x star plus epsilon, where epsilon is a very small value. So we're at our fixed point and then perturb it just slightly away. And we can determine if we apply our mapping function, do we move towards or away from our fixed point? So going back to our example, let's consider what happens near our fixed point x star equals to 0. So then we're going to start at x star plus epsilon equals to just epsilon because our x star value is 0. We plug that into our map. So it would be f of epsilon is equal to 2 epsilon times 1 minus epsilon. And so now we have to evaluate this. How does this compare to our previous position? Well, we recognize that 1 minus epsilon, this is approximately equal to 1 because epsilon is very small. And then we have this 2 out front. And so it's reasonable then to assume that this is approximately equal to 2 epsilon, which then of course would be greater than epsilon. This would indicate that taking one step from this perturbed position moves us away from x star equals 0. So we could eventually show this, right? We could say, okay, well, what if epsilon is equal to 0.01? Well, then we would say, okay, that's 2 times 0.01 times 0.99, and that's going to give us a value of 0.0198, which is greater than the 0.01 that we've started at. In fact, almost double, which is what we would expect. Therefore, our x star value at 0 is unstable. But we can already tell that this is a bit of a cumbersome approach if we were to repeat this for our x star value of 1/2, we might get a lot more values that we have to sort of parse through and figure out, okay, is this moving away from or towards our fixed point? So there's an alternative approach. A test for a fixed point stability of the map f of x star requires considering the magnitude of our derivative of f. If it's less than 1, the map is then stable at that particular x star value. If it's greater than 1, then it's unstable at that fixed point. And if it's exactly equal to 1, then it would be semi-stable. And that's a rare case which we're not going to really delve into too deeply. So for our case, our f of x star is equal to x star 2x star minus 2x star squared. So our derivative of this would be equal to 2 minus 4x star. And so to determine the stability of each fixed point, we would plug in the fixed point position, x star, into this equation. So f prime of 0 would be equal to 2, and f prime of 1/2 would be equal to 0. So this indicates that our 0 fixed point is unstable, and our fixed point at 1/2 is stable, which is exactly what we seem to see from that graphical representation at the beginning.